Today's session is going to focus on the data encoding techniques, which are also known as feature maps. And let me start by sharing my screen of the tablet. Okay, so looks like the screen sharing is enabled. And
Yeah, we can see it.
Gibran, is this looking okay?
Yeah, I think it's looking fine. We can see the shared
Okay,
screen.
perfect. So today's session is going to focus on data encoding techniques. And just to recall from yesterday, we saw that the two major methods in quantum machine learning, the one which we call variational quantum circuit and the other that we call quantum kernel methods, they invariably have two blocks of circuit. So one is that we represented with S of X that represents the classical data encoding part. And then there may or may not be an additional uh, parameterized block that is independent of the data, and the circuit might be initialized to a state, suppose a 0, 0 state. So today we are going to talk about this S of X part. Sometime I'll be referring to this as unitary U of X, sometime S of X, just to emphasize that this S of X is a unitary operator. Okay. And just to connect with the yesterday session, yesterday we were calling all of this block as U of X theta. So when it is just U of X, it means it's the part of the unitary referring to the data encoding part. The data encoding in quantum computing and quantum machine learning is actually one of the most critical steps because in quantum kernel methods, this actually implements not only the data uploading to quantum computer, but also a kernel map that transforms from one feature space X to the feature space uh, that is uh, the Hilbert space spanned by the uh, the Hilbert space in which U of X lives. So psi of X is U of X operating on some initial state psi naught. Many times this initial state is this zero state, but sometime it could be a state other than zero state as well. All right, so let's talk about data encoding and feature maps now. And let me just say that this data encoding or feature maps can be thought of in two equivalent ways. They are both equivalent, and sometime in some techniques, one way of thinking is better, and in some other techniques, the other way of thinking is better. But let me start with the main approaches, and then we will talk about various examples. So we can think about as uh, encoding a quantum state directly based on data. So this I'll call encoding directly into a quantum state. So we can picture the data uploading to quantum computer as preparing a quantum state directly based on this data. Or we can think of uh, data encoding as a Hamiltonian simulation problem in which the simulation time, it depends on X. So here we have like a state. We think of it as, encoding the circuit directly. And then in other ways, we can think of this state that is being generated from a Hamiltonian H that is applied to some initial state psi naught, where this x, f of x, which corresponds to time in Hamiltonian simulation, is function of our data. And sometime, this approach is better, and sometime this approach is better in thinking about the data encoding techniques. So first, since this way of imagining things is simpler, so let's start talking about some example techniques based on imagining this as a direct encoding scheme. So the first example that we can take is, let's call it basis encoding. So basis encoding is perhaps one of the simplest way. For example, you have uh, data set like this. So let me also talk about conventions here. So when I'm putting one in bracket in superscript, that means one example, and then this two mean another example, and so on. And I might have like m examples. And then each of this vector x is actually a column vector itself. So I can write it like this. So x1, x2, and so on all the way to xn. So it's like there are n features and m examples in the data set. Sometime I'll refer to a particular example as xj, and the some uh, ith component or maybe kth component of xj as xjk. So this x superscript jk means that it's the jth example and it's the kth component. So suppose we have a data set like this, and one data point, I can upload it to the quantum circuit like this. Suppose it's and sometime I'll represent it like this as well. X1, x2, all the way to xn. When I know that what example I'm talking about, there might be a superscript missing. So if the superscript missing, it essentially means some jth example. Okay. All right. So with this convention, let's talk about an example. Suppose I have an example xj, like say 3, -4, and 7. So basis encoding means that I choose some number of qubits. Let's say I choose 4 qubits and maybe 1 qubit for the sign. And then I prepare the binary code for this. So for example, in 4 qubits, this 3 would be 0011. This 4 would be 0, 1, 0, 0, 1, 0, 0. And for this sign, so this is positive, I can put 1, maybe 0. And for minus sign, I can put 1. And then for 7, I can use 0, 0, 1, 1, 1. So I prepare this, binary equivalent of this data. And even if this is decimal data, I can reserve a few qubits after choosing a resolution after the decimal point, and then I can add bits to that. And then a quantum state, psi of x, let's say it can be a state with first x1 in binary notation and then x2 in binary notation, and then x3 in binary notation. So this would become 0, 0, 0, 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 1. So this is a state in which the data has been encoded in uh, its basis. And just to see how many qubits we need n plus 1 times n, where n is the number of feature. So let's say I have n for the magnitude, 1 for the sign, and then there are n feature. So this is the number of qubits that are needed for this circuit. And we can easily prepare this state. It's really easy. All I can do is start from 0 state. And if there's a 1 anywhere, I put an X gate. For example, there's a 1 here. So an X gate comes, then there's a 1 here, another X gate on the next qubit, and there's a 1 here. So there's an X gate on the third qubit, and then there's no 1, 0, 0. So this fourth, fifth qubit goes as it is, and so on. So we can apply the X gate if there's a 1 and no gate if there's a 0. There's a question in chat that I see. It's asking if n is the number of data points. No, n is not examples. N is the number of features. So m is the number of examples. All right. So any question about the basis encoding? We can see one easy thing about basis encoding. It's that if we talk about its characteristics, it's a circuit of depth 1. Really great circuit for near-term quantum computers because depth is 1. And the number of qubits that we need is given by this expression over here. So we do need a lot of qubits. That's the one major issue with this. And other than that, the circuit depth is really a nice feature for this technique. All right, so let's go to the second technique, and that's another one that is easier to imagine directly. We call it amplitude encoding. And in this case, what we do, let's say I have an example like x1, x2, x3, all the way to xn. So first of all, I normalize this data. And by the way, for basis encoding, we do not need to normalize the data. However, we have to be mindful of choosing this n, that this n should be such that we can represent the biggest of the number here. If there is a few numbers that are too big and all others are small, we might have to cut that number out. But other than that, we don't have to normalize the data. However, for the amplitude encoding, we first need to normalize the data so that it can be made the amplitude of a quantum state. So what we do, we prepare another state A, another vector from this by taking the square of all the data points, adding them, taking square root, and then dividing with it. So this becomes x1, x2, xn, and let's write it as a vector a1, a2, all the way to an. And if n is not some 2 power n, then we might have to extend this A vector by including zeros. It's called zero padding, so that whatever this new n is, this is equal to 2 power n. So that we can now use n qubits, where n is just equal to logarithm of this n, which is always less than or equal to log 2 of actual n, and we prepare a state, quantum state like this. A1, let's call, if this is, we can actually start it from 0 and 1, just for the case ease of numbering n minus 1, and then I can just use this easy notation that I from 0 to 2 power n ai I, where this is just the decimal notation for the basis state. So by preparing this superposition state with amplitudes proportional to our data points, we can prepare an amplitude encoded quantum state that is function of the data vector x. You see this, I think there's a question in this one. Should this be the mod square to take care of complex? Yes, if x is complex number, then we will have to take mod square. But I'm going to be assuming throughout, this lecture today, which is generally the convention, is that this x is real number. So we will always take this x vector to belong to uh, a real space of n dimension. So all of the numbers are assumed to be real. Of course, if they're complex numbers, we can easily take care of that. We can have maybe x1 real part, x2 imaginary part, x3 real part, and so on. But for this discussion, we are going to be taking it to be real. There's another question: how do we define the depth of circuit? So in classical networks, there is concept of depth, but not directly relevant here. But in quantum circuits, the depth means how many layers of circuits we have to execute. All right. So any question about the amplitude encoding? All right. So amplitude encoding is actually really great because of very few qubits that are required uh, to represent the state. There's only one big flaw with this technique, and that is that we all know that in general, to prepare an arbitrary state starting from zero state to an arbitrary state, this is an exponentially complex task. So the circuit depth is actually really huge, but we can reduce the depth by approximating it. And in Qiskit, we can easily just use initialize command and give it this amplitude vector. And with this initialization, we can initialize to this state psi of x approximately with these amplitudes. Okay, so circuit depth is not very good for amplitude encoding, but uh, the number of qubits are really nice. Okay, so in terms of scaling, just remember that there is a different scaling for this encoding because we have to make sure that all data points are scaled in such a way that their squares of the sums are at 1. And you can see that this is going to be resulting in a state with only real amplitudes because we're assuming x is real, so a is going to be real as well. All right, so let's talk about the next technique. We call it angle encoding. So for a single qubit, we know that its state can be represented in a standard form like this. Assume that you know this thing from basic quantum computing. So you see, there is this angle theta, and if we take these amplitude to be real, then for real amplitudes, this state can be written as cosine theta by 2 0 plus sine theta by 2 1. And we can actually use uh, this theta to encode our data as well. Suppose again my x vector is x1, x2 all the way to xn, and suppose I choose n qubits. Okay, so this is q0, q1 all the way to this n minus 1 qubit. And then what I do that for this qubit, I somehow this encode x1 and prepare a state cosine x1 sine x1, and for the second qubit I somehow encode x2 and prepare this qubit in a state cosine x2 over 2 0 plus sine x2 over 2 1, and so on. And by the way, I can easily do this because this state can be obtained by applying a rotation gate of around y-axis by angle theta on zero state. So this is nothing but ryx1. This is ryx2, and the last is ryxn. So it means the overall state psi of x vector is just the tensor product of states like this. So I can write it like this. So it's some xi over 2, 0 plus sine xi over 2, 1, tensor r. That this state is repeating on each qubit, and each qubit's is prepared in this state using RY gauge. So we need n qubits. So number of qubits that we need are equal to the number of features that we have, and we are able to encode the data in the angle in this state. Now, there is one issue, and that is that if this angle is more than 2 pi, the state would not be unique. So what we have to do is before we implement this, we have to rescale our x so that x is just between 0 to 2 pi, or equivalently, you can also scale it to be between 0 minus pi to plus pi. But you have to keep it in the range 0 to 2 pi so that each point is mapped to a unique stage. All right. So any question about the angle encoding? If not, let's go to the next encoding scheme. It's called the phase encoding. And sometimes it's also called Z feature map. And we'll see that why this is called this when we talk about the Hamiltonian simulation view of data encoding. So in phase encoding, I'll get back to the state of a single qubit. So we know that the general state of a single qubit is this. So instead of encoding in theta, we can also choose to encode in phi, and let's say keep theta fixed. So in this case, suppose we keep theta fixed so that it's cos theta by 2 is 1 over square root 2, 0 plus 1 over square root 2 exponential minus iota phi 1. And now, in this case, the state for first qubit that depends on first feature vector. Now, first member of the feature vector is 1 over square root 2, 0 plus 1 over square root 2 minus iota x1. And similarly, for the ith, it's going to be xi, and the whole state psi of x for the full vector is just going to be the tensor product of all states. And just to emphasize that this angle encoding give rise to a state which is a product state at the end. That each qubit has the joint state is just a state which is the product of individual states. Similarly, this phase encoding give rise to a product state because the total state psi of x is just psi of x1 tensor psi of x2 tensor so on. And this is one qubit, this is one qubit. All states are single qubit states. And we can easily prepare, by the way, this state from initial state 0. If I apply a Hadamard first, and then I apply a phase gate that is dependent on this X, feature, because Hadamard transformed the 0 state into 1 over square root 2, 0 plus 1, and the phase gate will add phase only to the state 1, and I can put a minus sign here, and it will not say anything to the 1 state. So with this method of applying a Hadamard gate and phase gate, we can prepare a phase encoded state. So in this case, we again need the same number of qubits as there are in as there are the number of features in the data vector. However, now the circuit depth is 2. Like there is a Hadamard gate and then there is a phase gate. All right. So one can ask that why do we have to encode either in angle or the phase? Why don't we use both of them? And actually we can do, we call it dense angle encoding, and we only need half of the qubits. Like there are 10 features, we only need 5 qubits because we can now, we are now going to encode one feature in angle and one feature in the phase of the state. So that's why it's called dense, because the data, no one qubit is carrying two classical numbers in its state. So there is a question, how do we replace phi with xi in exponential? So it's really easy because when you are applying the phase gate, so for example, in this case, what I can do is first apply an RY gate that rotates by an angle which is equal to x1. And then I can apply a phase gate that gives a phase x2. And if I apply x2 here, then I can use, a plus sign here. Okay, so the person who asked the question, is this clear enough? that you have to apply a gate and you can just use your data to tell it by what angle to rotate. So this phase gate is essentially an RZ rotation gate anyway. So this is an RY rotation, this is a Z rotation. So similarly, if we have, let's say, uh, four features in our data, we can use another qubits, and this rotates by x3, and then the phase gate gives a phase proportional to x4, and so on. So it's not just a notation. What we are saying that, you use phi to rotate the state of a qubit, but you have to tell it how much angle to use for the rotation. And if the angle is equal to the value of the x that you want to encode, then your point is encoded. If you give the value of the angle something else, then the rotation is according to that whatever phi that you provide. So it will be an encoded state and depend on psi of x1 and x2 if the rotations are according to this thing. All right, good. So, and you can see again that we will have to rescale our data again so that all features are within 0 and 2 pi for this to work. All right. So if we go on this way, so we see that let's say, for example, for these two qubits, we have been able to encode four parameters. And if we keep going with three qubits, we will be able to encode, x5 and x6. So we'll be able to encode six, parameters. However, we can actually do more than this. And the reason is this, that for a single qubit, we know that for so this new technique that I'm going to introduce, it's called efficient SU2. And the philosophy behind this is this, that for one qubit, the state is, something like this. There is a complex amplitude for zero state, and then there is a complex amplitude for one state. And you see there are a total of four parameters that define this state. So if I use four parameters, I can access a wider part of the Hilbert space than if I just use two parameters. I know that we have a restriction that A modulus square, B modulus square is 1, that essentially reduces the number of parameters to 3, but still it's more than 2. Similarly, for 2-qubit state, I can actually have 8 parameters, because we have four complex numbers, and then they both all complex numbers have a real and imaginary part, so there are 8 parameters, and of course at the end there are only 7 independent parameters because of this normalization. But usually, this additional restriction we are applying in many encoding schemes anyway. For example, in the amplitude encoding, when we normalize the data, we essentially reduce it by 1 parameters. So anyway, so it means we can do better than this dense angle encoding as well. And that also makes sense because with this dense angle encoding, we still have a product state. A product state in which there is a one qubit state that depends on x1, x2. There's another qubit state that depends on x3 and x4. So we haven't really taken advantage of the entangled or the superposition states in multi qubit Hilbert space. So this efficient SU2 takes advantage of this thing. And what it does, it tries to encode as many parameters into the state as are possible. And then, of course, uh, if you start repeating the encoding, for example, even here, I can put this block right after this block as well. And like I can encode more parameters into this qubit, and maybe I can put this block again on the same first qubit. What that does is that the state is no longer unique for a given set of parameters. But even by keeping a unique state for each set of input data, we can still do better than this dense angle encoding. And that give rise to an encoding scheme that efficiently encode the data. And when I'm going to do the coding exercise later on, I'll show the syntax for this. There's, somebody has asked what's SU2. SU2 is a special unitary, a 2 by 2 for this, single qubit operation. This is called SU2. Any rotation is an SU2 for a 1 qubit. If you are afraid of this thing, don't worry too much about this. This essentially means that, taking advantage of all of the parameters that we can use to come up with a unique state, or we can access a better part of the Hilbert space. Okay, so let me take another view of these encoding schemes, because this is in terms of understanding and coming up with new ways of encoding data. This is almost as far as we can go if we just think about directly encoding the data into the state. There is another other view of data encoding, and this is based on Hamiltonian simulation view. And actually, all these methods that we just studied for encoding, we can reimagine them as a sort of a Hamiltonian simulation happening. And not only that, we can come up with new techniques of encoding data into our circuits using this Hamiltonian simulation view. And just to briefly recall, the Hamiltonian, if we have a Hamiltonian of a system, then what I essentially mean from Hamiltonian simulation is this, that suppose I have a Hamiltonian H, and then I apply it to some initial state psi naught, and I let it evolve for time t is equal to f of x. So this evolution time is now a function of my input data, the data that I want to encode. So if I choose this simulation time based on this, input data, and also choose a Hamiltonian in various ways, I can prepare various, types of quantum states that encode this data. Let me take a few examples to, make it more explicit. So number one, let's take the simplest case, and let just take the Hamiltonian as a single qubit operator, let's say poly Z operator. It's a sigma Z operator or Z gate. And then let's take f of x as just x by 2, that this is some feature x, and this f of x is just x by 2. So this is a single qubit operator. So the data is going to be encoded into a single qubit, and my state would look like something like this. And suppose let's keep psi naught like psi naught right now. So this thing, let's work it out. And I'm going to do it quickly because I think most of you would have encountered this in quantum computing basics anyway. So I can expand it using Fourier series, using Taylor series. So identity minus iota x by 2 sigma z plus half, then minus iota x by 2 sigma z square, and then 1 over 6 minus iota x by 2 sigma z cube, and so on. And since this is not only Hermitian, sigma z, that's also unitary operator. This means sigma z square is identity, sigma z cube is just sigma z, and so on. So it means all of these terms, there are only terms with identity, and then there are terms with sigma z. And if you combine the coefficients of identity, we can see that they add up to cosine x by 2. And if I combine the terms with sigma z, they add up to sine of x by 2. And if you write its matrix form, like this, identity is 1, 0, 0, 1, cosine x by 2 minus iota, and this sigma z is 1, 0, 0, minus 1. This is nothing but exponential minus iota x, 0, 0, exponential iota x, which is a z rotation gate by angle x by 2. No, by angle x. Let's see if everything is so x by 2, and this should be, yes. So this is the z rotation method. So it means that this Hamiltonian with the uh, this f of x, and let's say I take psi naught to be a plus state. Suppose psi naught is a plus state, 1 over square root 2 0 plus 1 is one data encoding scheme. And if I implement it, and by the way, this RZ gate, if I take exponential minus iota x common, this becomes 1, 0, 0 exponential 2 iota x and exponential minus iota x. So this is just a phase gate with angle 2x. So this becomes, I can get this plus state by applying the Hadamard, and by, let's forget about this global phase, and then this is just a phase gate like this. And if you see closely, this is nothing but the z, uh, which we called the phase encoding, right? This encodes, because if this is plus state and you apply RZ gate to this, or this, P gate, this will transform to a state like this, 0 plus exponential iota 2x 1. So the information is being encoded into the phase of this state. So this is the phase encoding, but we also call it as Z feature map, because this is being generated by a Hamiltonian, which is a sigma z. And now you can easily see that I can generate many other encoding schemes as well. Suppose I still take f of x as x by 2, but this time let me take Hamiltonian as sigma x, and let's take this psi naught initial state to be 0, and this will result in a state like this, exponential minus iota x by 2, sigma x and 0, and this is nothing but the x rotation gate by angle x applied to this 0 state, and this x, if I open it, this becomes cosine x by 2, 0 minus iota sine x by 2, 1. So this is almost like an amplitude encoding scheme, except that we now have a minus iota instead of plus 1. So you can call it like a complex amplitude encoding scheme. So just 0 state, and you apply an x gate with an angle x. And then if you have more features like this is, let's say, first feature, then you can have an x gate with an angle x2 on the second feature, and so on. Similarly, the angle encoding scheme can be reimagined as generated by a Hamiltonian sigma y applied to this initial state of 0, because this is equal to an ry by an angle x applied to this 0 state. So this is our usual amplitude encoding scheme. And if you want to think about the phase encoding, so phase encoding was nothing but like two circuits coming right after each other, and we can think of them as like the dense angle encoding can be recovered using this Hamiltonian simulation scheme. If we imagine an x by 2, and then we have a Hamiltonian that could be a sum of sigma y and sigma c. The only thing is this, that this is not exactly equal to, but approximately equal to minus iota x by 2 sigma y, because these two don't commute, and we can't write it like this, but actually we can come up with an even more general Hamiltonian. It's if we want to do exactly reproduce DAE, we can have an x1 by 2 here with the sigma x, and x2 by 2 with sigma z, and apply to state 0. So this part roughly generates the angle encoding, and this part generates the phase encoding. All right, so far we only talked about single qubit encoding of one feature. However, this Hamiltonian simulation actually gave us now a way of encoding data into the joint states or in entangled state. We talked about this in efficient SU2, where we said, okay, we can encode data, into more parameters. And let's now talk about one systematic way of encoding data, not only in the individual qubit states, but encoding data into the correlations of qubit states. And let's see how we can do this. For this, let's take a Hamiltonian, simpler Hamiltonian, sigma z, and suppose I have two qubits. So let's say there's qubit 0 and qubit 1, and I'm going to apply a minus iota f of x h on these two qubits, and suppose I get a q0 prime and q1 prime state out. Where f of x, I'll talk about f of x later. So there are two qubits. So my f of x right now is essentially function of x1 and x2. So there are two qubits, and let's say I'm trying to encode these two features into it. I can actually have x1, x2, and maybe x3, x4, etc. But let's say I have x1, x2. Now, this means to work out the circuit for this, I have to work out what minus iota f of x sigma z is. So I can expand it in a Taylor series just as we did for sigma z, like this: iota minus iota f of x sigma z tensor sigma z plus half minus iota f sigma z. Let me just not write tensor, it's a little bit cumbersome writing it again and again. And we see again that this sigma z tensor sigma z square will be identity. And similarly, in the next term, sigma z tensor sigma z cube, it would just be sigma z tensor sigma z. So we can similarly combine it to get cosine of f of x into identity minus iota sigma z tensor sigma z sine of f of x. And let's now see how we can implement this gate. Okay, so for this, let me construct the truth table for this. So suppose I have these states Q naught, Q1, Q naught. Maybe in this course, let me write this Q naught on the left because most people, that's what they do. Even though in Qiskit, it's actually the other way around. So let's say this is state 0, 0. So if I apply this thing to minus iota f, sigma z tensor sigma z to state 0, 0, this means that I apply identity to this. So I get 0, 0 cosine f, and then I apply sigma z to the 0, 0, and sigma z on 0 is just 0. And so this, and just for the next example, sigma z on 1 is minus 1. So this sigma z on 0 and this sigma z and this 0 is giving just plus 1 plus 1. So I get minus I 0, 0 sine f, and we can take this 0, 0 common and it becomes minus iota f. So it means for this, the output is just a scalar multiple exponential minus iota f. And if the input is 0, 1, if 0, 1 is coming here, so let's say this is 1, in that case, I'll get a plus 1 when I apply the sigma z and 0. But when the second sigma z applied on 1, I get a minus sign. So this becomes plus. So this becomes iota. So for 0, 1, we get 0, 1 exponential plus iota f. And similarly, when input is 1, 0, there is only 1, 1. So we get a minus sign only once. So the sign flips. So we get exponential minus 0, 0 iota f. And then when the input is 1, 1, now when the input is 1, 1, we get a minus sign from this and minus sign from this, which will make this as a minus sign. So we get 1, 1 exponential minus iota f. So we have to think of a circuit that gives us this truth table. And we can see that we can get this truth table from this circuit easily. The reason is this, we have to think like this. If both qubits are 0, 0, or if both qubits are 1, 1, we get a phase with minus sign. And if either one qubit is 1, we get a phase with plus sign. So it means I have to apply a phase gate, a phase F, if one of the qubit is 1. And let's see what happens. If this is state 0, this is state 0. This control X will not work, so I'll get 0, 0. So if this is 0, 0, then this actually instead of phase gate is not going to do the job. Let's use the RZ gate, the rotation around Z axis. So, okay. So the RZ gate is like this. If you apply to 0 state, you get exponential minus iota f, and where you're applying a rotation by f. And if you apply the RZ gate to state 1, you get exponential plus iota f, which we can see from this matrix as well that we derived here initially in the Hamiltonian simulation part. You see this matrix. So for 0 qubit, this is the phase, and for 1 state, this is the phase with plus sign. So coming back here, so this RZ gate, since this qubit is 0, this will give This will keep it 0, 0, but give us phase with minus sign, and we get 0, 0, exactly what we want. Now, if the input is, use this blue, so if the input is 0, 1, what happened? This is 0 and this is 1. And because this is 1, the RZ gate will give a phase with plus sign, but keep the state as 0, 1. And the 0, 1 goes over here. So 0, 1 remains 0, 1, and I'll get positive phase. If it is 1, 0, so if it is 1 and 0, so this is 1, this is 0. So to 0, this actually this will not be 0, because if this is 1, this is 0, control X will be active, and this will become 1. And for 1, this RZ gate will give a minus sign, and then I'll get 1, 1 here, but then this control X will make this 1 back to 0. So we get 1, 0 with the positive phase. With the 1, we get positive phase. And but when it's 1, 1, when it is 1, 1, we get 1, 0, and 0 gets a negative phase. This becomes 1, 0 with negative phase, and then this control X 1, 0 becomes 1, 1 again. So we 1, 1 goes to 1, 1 with the negative phase. This is a very important circuit in encoding schemes. It's called an RZZ gate, and it encodes these two feature points. It's important because uh, this prepares a state in which the information is encoded in a joint state. And this is classically a hard circuit. So if I have, like, say, n qubits, so classically we can prepare this state using RZZ type gates with the, n type, n or roughly order of operation, but classically we will need exponentially many steps to compute the state. However, just as a caution, if we have a classically hard state, it doesn't mean that we will get a quantum advantage, but at least there is a possibility. So that's why this is sometimes called ZZ feature map, because of this RZZ gate, which is actually just this gate. So coming back to the total ZZ feature map, in the total gate, so there's a question. I'm a bit confused that qubit is a superposition of state 0 and 1. Then how we can say Q0 is 0 or Q0 is 1 is a qubit. So we are taking only the basis state here. So in general, whatever the state is coming here is a superposition state. But when we are trying to work out the gate, we are just taking one basis state at a time. So that makes the logic easier to follow. Okay. All right. So the ZZ feature map actually works like this. In general, it's defined. We apply a Hadamard gate to prepare a plus state. Then we apply a Hadamard gate to prepare a plus state, and then we apply a phase gate, parameter x1 and x2, another phase gate, and then we encode this feature through the RZZ gate. And there's still another choice that we have to talk about, this f of x. So f of x, actually there are many ways to choose. A popular choice, which is a default choice in Qiskit as well, we take it to be pi minus x1 multiplied by pi minus x2. So this f is a product of x1, x2, which means that we can't separate the exponential, into two parts. And just an emphasis again, x1 and x2, they have been scaled to be between uh, 0 and pi for one-to-one correspondence and getting a unique state for each pair of the expectation values, each pair of the features. All right, so now you see that how we can, come up with ways of uh, constructing feature encoding maps. You can actually easily see that we can prepare, let's say, an XY feature map as well if we want, uh, because XY feature map would be where our Hamiltonian is sigma x tensor, let's say sigma y, and maybe uh, xz and so on. However, we have to remember this very actually good and important thing about Pauli operators, that let's say if I have sigma x tensor sigma z, I can write it as a Hadamard identity exponential minus f of x sigma z tensor sigma z. So actually, both x and y Pauli operators, they can be written as sigma z times some simple unitary. For example, sigma x is just Hadamard, sigma z Hadamard, and even if there's a y, so sigma y would just be a Hadamard s and s dagger Hadamard. So if you essentially can implement this ZZ feature map, all other feature maps are encoded in, they're almost like this feature map if we are talking about two qubit maps, because up to this unitary, they're essentially the same. So that's why this ZZ feature map is very popular, that once we have this ZZ feature map, we're essentially implementing other feature maps as well. That if we have a parametric circuits, so like there is some parametric circuit, and then there is this ZZ feature map, and then there is another parametric circuit. So this essentially implements all as sigma x, sigma y, or any two qubit circuit that you can imagine. Because by tuning this theta, we're essentially tuning these unitaries, and then this maps to any of the feature map for two qubit that we talked about. Okay, so any question about this ZZ feature map? Okay, I'm going to close this theory part and start to walk you through the code. But just one very important point that I just briefly want to make is this, that if we have uh, a Hamiltonian that is sum of two terms, suppose this is sigma xy, this is sigma xz, or maybe this is zz, this is z1, z2, this is z2, z3. So in general, we can't write it as h1, h2. However, using the Trotter scheme, we can approximate it like this, which means that I can implement this sort of general Hamiltonian by implementing the repetitions in the circuit. For example, I have, say, a feature map ZZ between two qubits, and maybe there's a feature map, ZZ feature map between qubit 2 and 3 and so on. So like this is sort of implementing one layer of this Trotter term, and then the second layer is implementing the second term of this Trotter term and so on. So this repetition that we usually implement in quantum machine learning circuit, it helps us to implement more general Hamiltonian, because we can imagine each layer to be implementing one of the terms in the Hamiltonian. So with this, let me pause for any questions before we go over the code.